Hi everyone, and welcome to the Nanosurf Python API webinar. Today we will learn how to install the Python environment and how to use Jupyter notebooks to read and analyze the data stored in Nanosurf NID files. We will also look into the Nanosurf Python package and learn how to control our AFMs with Python. I will show you a few application examples where Python is useful, and we will learn a few things about building custom user interfaces. As a short introduction, I would like to say a few words about Python. Most likely, you already know that Python is an interpreted high-level and general-purpose programming language, which emphasizes code readability. It is the closest thing there is to the executable pseudocode. And I think this readability is one of the biggest advantages of Python, because we spend more time reading the code rather than writing it. Another great thing about Python is that it's like a glue between different technologies. It's easy to combine many different languages and frameworks in one Python project. So it is a great language for prototyping. Having this in mind at Nanosurf, we chose Python as our language of choice for the scripting. Other advantages of Python include its universality. It could be either backend, front-end, or web development language. It is easy to learn, and not surprisingly, it is often taught at schools and universities. It has a very large user base, so it is a popular language. And as a result, it has a huge collection of libraries. And if you can think of any functionality you might need, it is probably already written, so you don't need to invent everything by yourself. Now I will say a few words about getting the Python up and running. It is very easy. You go to the python.org and download yourself a 64-bit Windows installer. I suggest installing it for the current Windows user and not to install it for all the users. As the development environment, I suggest Visual Studio Code, also a 64-bit user installer. If you're already comfortable with another code editor, that is fine too. You can keep using the editor which you like, but I will be using the Visual Studio Code in this webinar. Once your Python is installed, it is good to test it by opening a command prompt or Windows PowerShell and typing Python there and pressing enter. You should see this welcome message from the Python interpreter. Once this works, you can install Jupyter notebooks by typing pip install notebook and pressing enter. Now, to start using Python comfortably with our code, you would need to install a list of other packages in the same way by using pip install. Some of those would be installed automatically as dependencies to the Nanosurf package. And for the PyQt graph, you have to get the developer version from the GitHub. All of those you will need only if you like to build user interfaces. But if you only want to control your AFM, you would just need to install the Nanosurf package, and all the dependencies will be installed automatically. Now I will look at loading our data files into the Jupyter notebooks and doing basic data processing. To read the NID files, you would need an NSF Open package, which is developed by Edward Nelson, our application scientist in the United States. And now I will show you how to use this package to read your data. For this, we made a few examples for you, and let's look at them now. Here's the list of the Jupyter notebooks examples. There are 6 of them, but today I will show you only 2, the force spectroscopy processing and the lateral force image processing. To start the notebook, you have to shift right click inside of this folder and open the Windows PowerShell window here. Now in the PowerShell, you have to type Jupyter notebook and press enter. And the Jupyter server will open in the browser window. In this window, you will see the list of the files in the folder. Now here we see the list of the folders, and you can go inside of every folder and look at the files there. So here in the force spectroscopy, you see there is the force spectroscopy notebook. Then you see the data, the spectroscopy data. And then there is also the force spectroscopy Python code, which is exactly the same as the notebook, but just without the markup. Now let's open our notebook. In its first line, we import our reader object from the NSF open, and let's call it the AFM reader. I also import some operational system module and the NumPy for the operations on arrays. And also not to forget the PyPlot if you want to plot your data. So later on, what I do in this cell, I'm listing all the files in the folder that satisfy a certain requirement. So in this case, I'm looking for a word spectroscopy in the file name. So as you can see, in this folder, there is only one file with such a name. This is spectroscopy01 NID. And now I can use our AFM reader to read the data from the file into these two variables. So the AFM reader outputs two different structures. One is the data structure and the other one is the parameter structure. So now we can look inside of the data structure and see how it looks like. Now the data structure is a dictionary, and this dictionary contains other data structures which can be identified by their keys. On the top level there are only two keys, the image and the spec dictionaries, and each of those dictionaries has two other dictionaries, the forward and backward. And in turn, each of those has its own dictionaries inside them. Well, these are not actually the dictionaries, these are the arrays with our data. Now the actual set of keys on the lowest level, it depends on your measurement. So what are you doing? What kind of measurement are you doing? So it's not necessarily there will be just this set of keys. So now I need to load the more limited set of data that I would like to plot. So I would like to plot the adhesion data, and for the adhesion set data I need to collect all data, spectroscopy, backward deflection array. And also I need an x-axis when I plot my data. So as x-axis I would like to use the z-axis, so which is an spectroscopy backward z-axis sensor. So now that I have my data, I can plot it. So I'm plotting it. And when you plot it, so the whole curve is of course much bigger. So let me show you that. So if you don't have any limits set on your plot, so the figure auto scales, but so you don't really see what's happening here in this part of where what we're interested in. So then I set up the XY limits of the figure so I could see it much closer. Now I also would like to calculate the adhesion force at every point. So here it's just the minimum of the curve, and I add this minimum for each curve into a separate array that I call adhesion force. And now that I have this array, I would like to do some statistics on it and plot it as a histogram. So now I have the mean value and the standard deviation here. So this was the basic processing of the force spectroscopy curve, and now you can build your own routines, more complicated routines based on that. So now let's switch to the lateral force example. So again, we're using the same logic. We would use the NSF open library to read our data, and we use NumPy and PyPlot to plot our data. Now, to visualize the friction forces, we had to look at both directions of the lateral force channel. We have to look at the image forward friction force and image backward friction force. So we load the data into these two variables, and we need to find the sum and the difference between these two channels. And usually there is a small offset between the forward and backward. You can either find it with trial and error, or you can also automate it using the convolution functions. And there are examples on the internet how to do that. Also, you have to build the XY axis because in our image file, the axes are not stored as arrays, but as two values, the minimum value and the range. And using these two values and the number of steps, you can rebuild the XY axis because you need them when you want to plot your image. So now that I have the axis and I already loaded the data and I calculated the sum and the difference, so I can plot our friction forces, and then you see in the sum, you cannot see the clear contrast of the friction, but in the difference of the lateral force measurement, you can clearly see the visualization of the friction forces. So this is all that I wanted to show you about the using Jupyter notebooks and the NSF Open library. Now let's look at some more serious stuff and learn how to actually control the instrument. For this, we would use the Nanosurf Python package. What I will show you today is only a small part of it. The full description of all the available functionality can be found in the programmer's manual. But this webinar will get you started. Our scripting interface is coming in two parts, the high level and the low level scripting. So let's start with the high level first. Okay, for the high level scripting, I will be using the Visual Studio Code editor and our Nanosurf user interface. I will have the Visual Studio Code open on the right and the GUI on the left, because the changes in the GUI that we're going to see now will happen mostly on the left part of the GUI. With the high-level scripting, you have full control over the user interface. Every button and every checkbox, every digital entry you can change with Python script. I will show you how this works now. So first, I import the Nanosurf module and I create the SPM object. Then I also create an application object in this SPM object. Inside the application object, there are all the necessary objects to control the GUI and the AFM instrument. Here's the list of the objects that I will use for this demo. The scan head, the operating mode, the Z controller, the approach, and the scan. I'm going to run the cell, and this will open the interactive Python window. In this window, I will see the output of my code. And also can run my code piece by piece, like in the Jupyter notebook. So it executes, and I see in the output that I am connected to the controller. So it means that there is a connection between the Python engine and Nanosurf software. So first I will make use of the application object, and I will change the file name of the image file that will be saved next. So here in the gallery you see that the default file name is image plus the index. I would like to rename this file to Nanosurf Python. So I run this cell, and here you go, the file name has changed. Now in the next cell, I would like to change the folder in which the gallery would save the files. So now the gallery folder is this, and I'm going to change it to the Python demo. So I run the cell. And now the gallery folder has changed. So next step, I would like to change my cantilever. By default, I have the stat 0.2 LUD here. So I run the cell, and the cantilever changes to dyne 190. Next step, I would like to change from the static mode to the dynamic mode and set the vibrational amplitude to 100 millivolt. So static force here. So you see the imaging changed to dynamic force, and I have free vibration amplitude of 100 millivolt. So the next step is to find the resonance frequency of the cantilever. This is an automated procedure with many steps in it, and we have to wait until it's over. This is equivalent to pressing this frequency sweep button and going through all the steps of the Cantilever frequency sweep. So in the next step, we can change the scan parameters. The image size, the time per line, the number of points, the offset, and the image slope. So I run the cell, and you see that the imaging parameters has changed. So next, we can change the PID controller settings. So now you see that gains has changed, the set point has changed, so you can really adjust everything with Python. So then in principle, you can start the approach, and while the approach is running, you can see the status of the approach if the system is in the approach mode. And the same for the scan. You can start the scan and you can check if the system is scanning. So I will not show you this now because it will take time, and I also don't have a sample below. But on our website there is a similar video where I'm going step by step through all these commands, and also this video shows you the approach and the scan routines are also working. Now I would like to say a few words about the low-level scripting. The low-level scripting allows the access to the AFM hardware on much deeper level, and it has more functionality. But this level of access could be also dangerous to the instrument, because you can do whatever you want, and there are almost no safety checks. Let's look at a few examples of the low-level scripts. We will look at the ramp generator and the signal analyzer objects from the low level. Again, I have the Visual Studio Code open on the right and the Nanosurf GUI on the left, and I made it narrow so we could see just the monitoring tab where we monitor our signals. And the first line is similar to what we already saw. We import the Nanosurf package and we create an SPM object. But we don't create an application object now, just a low-level object, the SPM low level. And I will not go through all the objects that exist on the lower level. I will look at just the two of them, the ramp generator and the signal analyzer, because to me these are the essential building blocks for many applications. Now I have defined the function for the ramp generator. It's going to ramp several AFM signals from the start point to the stop point. It's called ramp axis, and it's using the lower level object, the ramp generator. In the beginning we define the ramp, what signal will be changed, whether it's X or Y coordinate or tip voltage, for example. So then I set the start point, the stop point, and the time of the ramp. And then this function starts the ramp. And it returns me a status if the ramp is running or not. So I can ramp many signals at the same time. So here I will ramp the X, Y, and the tip voltage together. But I will choose different stop points and different times for them, for these ramps. The X I will ramp from 0 to 2 volts in 8 seconds, Y I will ramp from 0 to 3 volts in 4 seconds, and the tip voltage I will ramp from 0 to 4 volts in 2 seconds. Now let's see how this works. So you can see all three signals are moving with different speeds and go to different values. The tip voltage goes to 4, the X axis goes to 2, and the Y axis goes to 3 volts. And I'm also using the print function to see what is the status of the ramp. So all three ramps return true. So the ramp is working. Now for the lock-in I have defined another function which takes the amplitude and the frequency as its arguments. And we're using an object called signal analyzer from the lower level, and we use its instance too, because the first instance is busy with the tip doing the mechanical measurement. And I will be using the fast user output as the lock-in output, and I'm going to send the analyzer reference to this output. I already set the amplitude and the frequency are the arguments to this function, and as the input for the lock-in I will take user input 1. I have also physically connected the fast output to the user input 1 with the BNC cable. And below, I will make use of this function. I will set up the lock-in amplitude to 1 volt and the frequency to 1 kilohertz. So I'm going to run this cell and see that the user input 1 has changed. It's oscillating now. And so is the amplitude of the second lock-in. So it's 1 volt now, and the phase is almost 0. Well, because the impedance of the cable that is connected is 50 ohms, so the phase difference is expected to be close to 0. This is all what I wanted to show you today about the low-level scripting. It's just to give you a flavor how powerful the low-level scripting could be, that you can think of what kind of experiments you might create yourself. Alright, now that you have seen a lot of code, and some of you might be asking yourselves, great, but how this could be useful for me and my AFM measurements? Now let's have a look at some examples. The first obvious example is the positioning of the tip or the position of the stage. If you have certain locations on your sample where you would like to do something, you can load the position list into the AFM and do some work at those locations. For example, here we loaded the position list in the spectroscopy module and used the FluidFM cantilever to do microspotting on our sample. Now think of this as a possibility to do certain measurements at these locations, or to do the lithography. Because once your tip is at the surface, you can apply voltages, you can do local heating, or apply stronger mechanical force at this location. Now moving the stage is also something that pops up very often, and here I'm showing you a short video on how to move our 300mm stage with Python. The same procedure. I connected the controller first, and I will be moving the stage first in x-axis for 10mm twice, and move it back. And I will do the same thing on y-axis. The last application examples I would like to look at today is the switching spectroscopy Pfm. Often you would like to know local properties in piezoelectric material, and those properties could be measured by the switching spectroscopy. The idea is that you sweep the bias voltage in the shape of this triangular waveform consisting of short voltage pulses, and you measure the piezoelectric response at each pulse, but you are only interested in the value of the response when the voltage is off. This reduces the parasitic electrostatic interaction between the tip and the sample. And then you would get these hysteresis curves of the amplitude and the phase of the piezo response. They are called the butterfly curves. And from their shape and the amplitude, you can draw conclusions about the piezoelectric properties. This was long requested by our customers, and our application scientist Patrick Fredericks decided to program this by himself. I have to say he had very limited experience with Python and GUI building beforehand, but in 2 days he got the prototype up and running, and a few days more he spent on polishing his script and making it more user-friendly. So here you see the final script with the GUI and the measurement data of the switching spectroscopy Pfm. I hope this gives you a flavor of what you can achieve with Python, and that you are only limited by your imagination and your ideas, but not by the functionality of our API. Here are the few examples of the GUI-based applications that over the time we have developed for ourselves and for our customers. We use PySide2 and PyQtGraph to build these GUIs. You have already seen the switching spectroscopy app, and we also have a different way to control the sample stage. And the control app for our magnetic field generator is also fully built with Python. Internally, we have created a template for the Python application with basic user controls, the graphical data output, data saving, and the flow control, so your business logic doesn't block your GUI. And we would like to share this template with you. Later, we are planning to include it into our Nanosurf package. And now I would like to go through this template and explain the key functionality behind it. Here is how our GUI template looks like. It has various user controls on the left and the graphical data output on the right. What you can also see is that the data output has high update rate, and this doesn't slow down the GUI functionality. Now let's look at the files inside the project. The actual design of the GUI window is stored in the form UI file. This file can be edited by the Qt Creator software. This software you can download for free from the Qt website, and we will not learn how to use it today. There are many tutorials on YouTube teaching how to do that. The next important file is the main UI py. It is a description of all the controls that you have created in the form file and assigning those controls to be members of the main application class. The actual business logic is in the main py file, where all the actions on all the events are described as functions. The graphical data output widgets are created dynamically and they are described in the plots.py file. And all the auxiliary functions are in the misc.py file. We will not look at all the code right now, but I would like to say a few things about the flow control in your application. To make sure that the GUI doesn't get blocked by your business functionality, it is important to use timers and threads. The timer would be a periodically repeating function that has a small computational footprint, but has to be called periodically with a short time delay. Timers run on the main thread together with the GUI, and timer will still slow down the GUI, but because it is a small task, usually it is not noticeable. And a thread is an object that runs its functionality in the parallel thread. One would move computationally heavy operations to a parallel thread, and the thread test.py file has an example of such a thread. It is very basic, but it has pretty much all you need to start your development. This is all I would like to say about the GUI building, and we are almost at the end of the webinar now. To summarize this webinar, I have demonstrated you today that you could automate our AFMs with Python. You could expand the AFM functionality and make your life easier. You could also build your own GUIs so that other less experienced users could use the functionality that you have built. You can also analyze your data with Jupyter notebooks, and the best part, it's all free. This is all that I wanted to show you today, and I hope you have found it useful. I wish you best of luck in your development of your own custom applications. Daniel?